have a look at your worksheet, page 5. This is November 15 P41. Okay. So for page 5 of your topical worksheet, you have a charged particle P that is situated in a vacuum at a distance x from the center of a charged conducting sphere radius r. For particle P outside the conducting sphere, the charge on the sphere may be assumed to be a point charge at its center. So state Coulomb's law here. Okay. So basically what they just mentioned here is that you have one charge here, and then you also have another charge here. Okay, so in the first place, they just want to know first what is Coulomb's law. Okay, for Coulomb's law, this one you can actually copy back the definition from the notes under page 2, if I'm not mistaken. No, not page 2, page 3. Where you just say force between 2 point charges is directly proportional to the product of the charges and inversely proportional to the square of the separation. It's always worth 2 marks, okay? The first mark always comes from you saying that it's for point charge. And then the second mark, it comes from you saying proportional to product of charge and inversely proportional to square of separation. Those two together is what gives you your other mark, okay? The one that I wrote in my original work solutions, that one is something a bit different. Better not to use that. Just use this one. Let's just standardize the definition. Okay. So this is what Coulomb's law actually is. All right. Then after that, if you move on to part 2, they mentioned to you that the sphere and the particle P are both positively charged. State the direction of the force acting on particle P. Okay. So if you look at it now, your big charge here, the charge that produces the field is positive. And then you have some test charge that you place inside the field here. This is also positive. What do you suppose is the direction of the force? Because they are both light charges, they will obviously experience repulsive force. So for particle P itself, it should experience an electric force directed away because it's repulsive. Okay. So how do you word your answer here? You would just say the force is towards the right, is radially away from the sphere, or towards the east. Okay. Now the wrong term to use here, according to the marking scheme, is to use away from the sphere. Because supposedly you say away from the sphere, it could have meant many different directions. Mean you say they would say that maybe you mean something like this. Maybe you mean something like this or something like this. It's also still, these are considered away from the sphere. So it's not as specific or precise. So they don't want this one. They want it to be a more specific term towards the right, radially away from the sphere, or towards the east. Okay. And after that, if you were asked to state the position of particle P for the force to be maximum, now this one common sense will tell you the closer you go and place your particle P towards the other charge, the stronger the field, right? The closer your particle P is, in other words, if your separation decreases, your electric force increase, right? Common sense would tell you that, because the closer you place the charges together, the bigger your force will be. So by right, your maximum force ought to be when you go and place it all the way right next to your sphere. That's where you have maximum electric force. This is where you have Fe max, isn't it? This is true common sense now. But if you want to kind of deduce it out from an equation, you can do so also. Because you see, the electric force between 2 point charges, it was already mentioned to you, is 1 over 4 pi epsilon naught QQ over R square, right? So electric force is actually inversely proportional to R square if everything else remains constant. So here you can see that the smaller your separation, the bigger your electric force. So you try to make the separation as small as possible, your electric force will become big. So the smallest possible separation will be when it's just right next to your sphere. So you can just say something like this now. Your force is maximum at the surface of the sphere, or when your x is actually equals to r itself. Basically what they're saying is this, because your x is this, right? So when your x is equals to r, that's when your force is maximum. Okay. And again, the examiner's report also mention here, some answers to avoid would be you saying it's near the sphere or next to sphere. Near the sphere and next to sphere does not imply just right next to the sphere, because it could mean something like this. This one is considered to be near the sphere. This one also considered to be next to the sphere, but not at the surface of the sphere. So your force is not maximum. Okay. So that's just one thing to take note of. Okay, then if you move on to part 3, they are asking you right now, find out the ratio of the force on particle P for these 3 different distances. So, sorry, for these 2 distances, when x is equals to r and when x is equals to 4r. What is the ratio of the force on particle P itself at r and 4r? So you consider a case like this now. So your case here is that you want to consider what is the electric force at x equals to r and x equals to 4r. So what's the ratio of the electric force here and here? Okay, what's the ratio of the 2 forces here when your separation is r and 4r? Okay, so for these 2 positions here, we already know that the electric force can be calculated by this equation. Fe is 1 over 4 pi epsilon naught times qq over r squared, right? So in our case here, there are certain things that you can say is constant here. The 1 over 4 pi epsilon naught obviously is already a constant. The q that you have here is obviously going to be a constant too, because no matter whether you put it at r or 4r, the 2 charges are actually still the same thing. So you could have actually say that q and q constant, Fe would therefore be inversely proportional to r squared. And then after that, from there, you can actually find out your ratio, where you say something like this. Your Fe at r, let's just call this Fr, to Fe at 4r, let's just call this 4r, would just be, okay, maybe I shouldn't make things more confusing. You could probably just write it as this now. F2 to F1 is equals to 1 over R2 squared to 1 over R1 squared, giving you R1 squared over R2 squared. This is the ratio of the forces. It's actually the ratio of your separation squared. Okay, so case number 1 is probably this one. This one is case number 1. Case number 2 is probably this. Okay. So in your case, if you try to sum in your values now in terms of the separation, R1 is actually 4R, but don't forget to square it. Case number 2, separation for case number 2 is supposed to be just R. Again, don't forget to square it. So eventually you will notice that you're supposed to get an answer of 16 for the ratio. Okay. The complete working is something like this now. identify what's the equation common to both positions, identify what is constant, and then work out a ratio. Then after that, you will get your answer. Oh, here I worded it differently. This one I say fe1 to fe2 is equals to x2 squared to x1 squared. This one here is me considering R as case number 1 for R as case number 2. But regardless, you actually still get back the answer as long as you don't go and misunderstood which separation is for which. Okay, so eventually your answer will just be 16. Okay, that's for this particular question. And if you're okay with that, I'll move on to the next one. Okay, the next one is in the next page here. Let me clear off this diagram here. Here they mentioned that when the charge on the sphere is 6 times 10 power minus 7 coulomb, the electric field strength at the surface of the sphere is 1.5 times 10 power 6 volt per meter. An electrical breakdown or spark would occur when the electric field strength at the surface of the sphere exceeds 2 times 10 power 6 volt per meter. Determine the additional charge that may be added to the sphere before breakdown occurs. Okay, so what they basically describe for you is this. Your charged sphere initially carries a charge of 6 times 10 power minus 7 coulomb. Let's call this Q1. 6 times 10 power minus 7 coulomb. And then the electric field strength at the surface is actually 1.5 times 10 power 6 volt per meter. Okay, they mentioned that a breakdown, electrical breakdown, sparks will start to fly when your field strength at the surface of the sphere exceeds this value here. Okay, so here they mention something like this. Yeah, a spark will tend to occur once the field strength exceeds a certain value. What they want to know from there is how much additional charge must be added to the sphere before breakdown even occurs. So here, your electric field strength, this E1 equals to 1.5 times 10 power 6 volt per meter. You're trying to increase it to E2 equals to 2.0 times 10 power 6 volt per meter, because this is where you have your electrical breakdown occurring. So when you increase your E1 to E2 here, you would obviously have to increase your charge also to some value. You have to increase it to some unknown value here. So what the question really wants to know here is, from Q1 to Q2, what was the additional charge that you had to add in? Okay, the term here is the additional charge that you need, not the final charge itself. They want to know what is the additional charge that you had to add in. They want to know what's delta Q here. Okay, now before I go through the calculation, let me just explain a little about what is your electrical breakdown or your spark. You consider this, if this is your sphere and it is positively charged, for example, if you go and increase the charge so that your field strength increases, suddenly you will have some spark occurring. That spark occurring is actually from your air molecules. You see, around your sphere here, you have air molecules that are floating around your sphere. Okay, but your air molecules consist of a positively charged nucleus and negative electrons that are orbiting around it. Something like this. Okay, this one is your A molecule, just one of the A molecule represented here. So if you consider the electric force acting on your A molecule, there's actually electric force acting on your nucleus as well as electric force acting on your electron, but they are going to be acting in opposite directions. For the nucleus itself, your electric force will be acting away from your sphere, but for the electron, it will be acting towards the sphere. You see, they are acting in opposite direction here. So the thing that can actually happen here is this. If your Q on your sphere increases, your field strength will increase. That will in turn cause the electric force acting on your electron and nucleus to increase. So if Fe is too large, the electrons can be stripped away from the nucleus, causing sparks to be produced. Okay, that is what we mean by the spark or electrical breakdown here. Is when you increase your charge enough so that the electric field strength becomes strong enough so that your electric force is also correspondingly strong, such that it is actually stripping away the electrons from your nucleus. So when your electrons get stripped away from your nucleus and start to move towards your sphere, that is what you are seeing as a spark here. Okay, so that is what we can actually say from here. All right, so how do I know this relation here? It's mainly because of something like this. If you remember, E is equals to 1 over 4 pi epsilon naught QQ over R square. You can see that if Q increase, E obviously increase. And then you look at another equation, E is equals to FE over Q, which I say FE is equal, in turn equals to QE. If your E increase, your FE will increase. Okay, so the relations are related, they are actually interrelated with each other. Okay, so this is just some background knowledge on this. Now back to the question here. We are really just interested in the additional charge that is required. We need to first find out what is the final charge. So now, between the first case and the second case, we know that the equation for electric field strength would apply. E is equals to 1/4 pi epsilon naught times QQ over R square. It's already written here. Now in your case here, I actually wrote this slightly differently. Instead of writing it as R, I wrote it as X. Okay, so sometimes you may notice it being written differently. X or R, they're actually the same thing. They're referring to the separation. Okay, now in your case here, your X is actually this one. It's actually the separation between the center of the sphere to the surface of the sphere. This is your X. Okay, and this is your X. All right. So under both cases, your X is actually considered to be constant. It never changes because you're using the same sphere. So obviously the separation between the center and the surface will be the same. So X is constant. That will mean that field strength is actually proportional to Q. So the ratio of E2 to E1 is actually equals to Q2 to Q1. You know the field strength values, you know the charge values. You just submit in, you get this. 2 times 10 power 6 divided by 1.5 times 10 power 6 equals to Q2 over 6 times 10 power minus 7. Then after that, you can eventually find out what is your Q2. But this is not the final answer because the question wants the additional charge required. So you have to do one step of working, saying that Q2 minus the additional charge is the difference in the two charges, Q2 minus Q1. Eventually, you get the answer is 2 times 10 power minus 7 coulomb. This one would be your final answer. Okay, it's 2 times 10 power minus 7 coulomb. All right. So that's for this question. So have a look at page 13 of your worksheet. This is Bill 16P42. They're asking you, by reference to your electric field lines, explain why for points outside an isolated spherical conductor, the charge on the sphere may be considered to act as a point charge at its center. Okay, so what it's really just asking you is this, to put it simply, why sphere can be considered as point charge? Why sphere can be considered as a point charge? That's what the question actually meant. How do you know that you can consider a spherical conductor, or rather just a sphere, as a point charge? Okay, so it's actually something related to what I mentioned to you earlier during the lesson. If you have a sphere with size and volume and you want to draw the field lines around it, the field lines must always be drawn such that it makes perpendicular contact with your surface. Okay, it must be 90-degree angle like this. So as a result of it having to maintain a 90-degree angle with your contacting surface, your field lines will always tend to appear radial. Okay, it's as if it's coming from a point. All right, so you extrapolate the field lines further into your sphere, you will notice that it tends to terminate at one particular point, which is at the center. Okay, your field lines appear to be coming from the center of the sphere, much like that of a point charge. So that's why you can consider a sphere as being identical to a point charge. So how would you word your answer? You will have to word it in a manner similar to this. You will say that the field lines are radial and appear to come from the center, so it can be considered to act as a point charge. Okay, this is one way of wording it. You say field lines radial and appear to come from the center, so it can be considered to act as a point charge. The word appear to come from the point, appear to come from the center, this is actually important to be written. Okay, it seems yeah, so this term must be written. You don't write that term appear to come from the center, this answer will be marked as wrong. Okay, your field lines appear to come from the center. They don't actually come from the center, but they appear to come from the center. That is the basis of this answer. Okay, so there's also another different variation of the answer. This one is, rather than you saying that the field lines are radial, you just say that the field lines are perpendicular to the surface, and hence your lines appear to come from the center. Therefore, you can consider it to act as a point charge. Okay. The part where you say that the field lines are radial, or you say that the lines are always perpendicular to the surface, they are actually the same point. It's because the lines are perpendicular to the surface in the first place that your lines will always be radial. Or it's because your lines are radial that your field lines are always perpendicular to the surface. Okay. So that one should be all right. Now, if you move on to part B, two isolated protons are separated in a vacuum by a distance of x. Calculate the ratio of the electric force between the two protons to the gravitational force between the two protons. Okay, so in your case here, let's just consider what you've learned. If you're talking about electric force is, let me zoom in a little. You're talking about electric force is 1 over 4 pi epsilon naught QQ over R square, right? That means you're talking about gravitational force from one of the earlier A2 chapters you learned. It's actually GMM over R square, isn't it? Okay, so you have to make use of these two equations, Fe and Fg here, for two protons. So proton, you can consider this like, you can consider it like this now. You have one proton here, and then you have another proton here. Say the separation is actually x. This is what the question mentioned. They're separated by a distance x. And then the charge is just simply your elementary charge. Okay, this is called this Q, and just call this Q. Okay. I can call this big Q. I can call this small q following the equation here. But actually, there's no need to because you see, they're both protons. I can actually just assign them as having the same symbol. This one will be small q, this one will be small q. Okay. There's no need to assign two different symbols to them. Okay. So what you want to find out is the ratio of the electric force to the gravitational force. So these two protons will experience an equal and opposite electric force Fe. Okay, they are being pushed apart, but at the same time they will experience gravitational force. They are being pulled together because they have masses that tend to attract each other, right? Okay. So again, the masses also, you don't need to write big M or small m here because it's two similar objects. They're both protons. You can just assume that the mass are the same. So this one is just m. This is also just m. Okay, to make your analysis simpler. Okay, so if you're talking about the electric force right now between the two charges, it's actually correct to say this. Fe is equals to 1 over 4 pi epsilon naught. Q times Q here would just be Q squared because they're the same charge. Then the separation will be x squared here. Okay. Then you're talking about the gravitational force. It's supposed to be gmm over r squared, but because they're the same mass here, you just be gm squared over x squared. Okay. So now, if you're talking about the ratio of Fe to Fg, you just be 1 over 4 pi epsilon naught q squared over x squared divided by gm squared over x squared. Now, you will notice that the x here, the separation will actually cancel each other off. This x squared here will cancel this x squared here, eventually giving you something like this. You will get 1/4 pi epsilon naught 1/4 pi epsilon naught q squared over gm squared. Okay, this is what you're expecting to get. Right, so the ratio is actually going to be 1 over 4 pi epsilon naught q squared over gm squared. All you just need to do is to sub in the values. Okay, so the ratio of your charge, the charge of your proton is going to be 1.6 times 10 power minus 19 coulomb. Then your mass of your proton, you can actually get it from the second page of your data sheet, second page of your exam paper, is actually going to be 1.67 times 10 power minus 27 is actually this one here. Okay. Then your gravitational acceleration G, that's not gravitational acceleration. Your gravitational constant will be 6.67 times 10 power minus 11. And then also, rather than finding individually 1 over 4 pi epsilon naught, the data sheet has actually made your life easier when they go and straight away tell you what's the value of 1 over 4 pi epsilon naught. There's no need for you to purposely use your calculator, take 1, divide by 4, divide by pi, divide by epsilon naught. the question, the data sheet has already made your life simpler by just giving you the value straight. So usually it's better to just use that value. So 1 over 4 pi epsilon naught is 8.99 times 10 power 9. Okay, so these are all the values that you require. You just submit in. Don't forget to square where necessary. You eventually get your ratio as 1.24 times 10 power 36. Okay. The one that you see written in your work solution here, I actually didn't use this value straight. I actually multiplied the values individually for 1 over 4 pi epsilon naught. It's a bit tedious, so I would advise you not to do that. Just straight away use the values that has already been given. Okay, so that one will give you your answer. And then you move on to part 2. By reference to your answer in 1, suggest why gravitational forces are usually not considered when calculating the force between charged particles. So you already calculated the ratio. That ratio here is telling you the ratio of Fe to Fg. And it's 1.24 times 10 power 36. It tells you that the electric force is 10 power 36 times more than your gravitational force. So since your electric force is so much larger than your gravitational force, you do not consider your gravitational force here. Okay, so you will word your answer something like this. Since the ratio of Fe to Fg is 1.24 times 10 power 36, the electric force is very much larger than gravitational force. Hence, your gravitational force will not be considered. Okay, because from here, you can see that Fe is going to be 1.24 times 10 power 36 of Fg. So Fe is so much larger than Fg. Therefore, Fg is negligible. Okay,